Welcome, everyone. I'm here to walk you through the technical evolution of Apache Iceberg. By the end of this presentation, you will know the initial project capabilities, what features we added over the years, and what's ahead. I'm Iceberg PMC member at Apple. For the last 5 years, I've been working on Apple Cloud services, where my responsibility is to make analytics reliable and efficient at scale. I'm a technical lead for a team that introduced Iceberg to Apple, and I think we were the first team outside of Netflix to heavily invest into the project. And we onboarded our first production use case in 2019, and it still operates till this day. Today, we'll essentially talk about how the community progressed over the years. And in my view, we can split the project timeline into three different phases with their own priorities. The initial focus was on the core format spec, where a lot of work was driven by limitations in Hive tables. We wanted to create a format that would be free of those issues by design. We also wanted to lay the groundwork for the future developments as well. Then we transitioned into a phase of making Iceberg production ready. That means providing all sorts of connectors for engines, making sure that table metadata scales well as well, and providing tooling for admins to manage tables. I think we did a pretty good job in the first two phases. And right now we're in a phase of proving that an Iceberg Lakehouse can be as capable and as efficient as any proprietary data warehouse on the market. So we made substantial progress here too, but there are also gaps that we have to fix as a community. And I think this is what we're going to work on in coming years. I think it would be fair to say that Iceberg was created because of the frustration in Hive tables, which was the de facto standard table format at the time. And here I refer to the general idea of keeping a list of partitions in the meta store and then doing lists to plan your jobs or commit new versions. There have been various attempts to fix Hive tables by introducing new commit protocols, but none of those approaches actually solved the underlying problem. And what made things even worse, people were moving to the cloud. And they were moving to the cloud with the same technology they ran on-prem. And that added even more complexity and issues. So it was clear a new table format designed for the cloud would give us tremendous boost in performance and scalability. The first issue that Iceberg is designed to solve is reliability. In Hive tables, we didn't have a concept of a transaction, so we could see partial results as our job progressed, and we could also end up with a corrupted table state if there was a partial failure in our job. In Iceberg, on the other hand, every operation is an ACID-compliant transaction with configurable isolation level. Under the hood, Iceberg uses multi-version concurrency control, which means every time we modify a table, there's a new version of the metadata being produced, and engines, they pick a version they need, and then they stick to that version as long as it is required by the operation. As a consequence, you can also do time travel. So in your SQL queries, you can pick which version of the table you would like to select from. Iceberg relies on optimistic concurrency with a file-level conflict resolution mechanism. So if you have multiple operations that are trying to commit at the same time, Iceberg will implicitly check if those operations are in conflict. And the check is done at the file level, which allows us to modify the same partitions concurrently, as long as those operations are not in conflict. Another critical design decision was to avoid any list or rename operations to plan a job, to commit a new table version, and to do table management. Doing lists and renames in an object store is never a good idea. So we wanted to design the format so that those operations are not needed at all. Another Iceberg feature is the ability to keep metadata per file. In particular, we keep min-max values for different columns, and this enables us to filter files at planning time without opening the footers of those files. Even if you have a petabyte scale table and a cluster with just a few nodes, you can still execute highly selective queries as long as you have proper partitioning and ordering of data. Iceberg also changed the way we work with partitioning because Hive partitioning is broken in a way because it is explicit. Let's consider a very common example where we have a timestamp column and we would like to partition by day derived from that timestamp. In Hive tables, we would probably need to create an extra column, call it event day, and populate that column every time we write to this table. What is even worse, we would have to add extra predicates on that partition column so that we can benefit from partition pruning, which puts a lot of complexity on the user. And the underlying problem here is that the format itself doesn't really know about the relationship between these two columns and that one is derived from another. As a consequence, we need to know how the table is partitioned in order to query it efficiently, which, as you can imagine, it's very easy to miss, and you may end up scanning the entire table. In Iceberg, on the other hand, you have a set of transforms which you can use to define partitioning. So in this example, I'm using the days transform on top of the event time column. And under the hood, every time I write to this table, Iceberg would derive the partition tuple for new records and store that mapping in the metadata. So whenever I query this table, I don't have to reason about how it is partitioned. I just focus on my business logic, and Iceberg takes care of the rest. What is even more, Iceberg tables can support multiple partition specs at the same time. So for example, if we create a table and then in 2 years, the existing partitioning doesn't really work anymore for the incoming data, you can choose to evolve the partitioning spec. And you can do that by adding, dropping, or replacing partition fields. Whenever we do that, the existing data stays in place. So we're not actually rewriting that. Instead, it is still persisted using the old partitioning spec. We simply created a new spec that we are going to use for the incoming data. And Iceberg internally keeps mapping for every file. So partition pruning would still work in both specs as well. And last but not least, Iceberg provides you reliable schema evolution using column IDs. Column IDs allow us to avoid any edge cases of tracking columns by name or by position so that you can add, rename, reorder, drop columns without any side effects like you would expect from a normal database. All of these features that we just talked about were available in the project from early on. And they not only allowed us to fix Hive tables, but also added a lot of advanced technology to our data lake. So it was time to make it production ready. The first phase that we heavily invested is a set of connectors. When Iceberg was released, it didn't have, for example, support for Spark SQL because we couldn't integrate with the data source v1. As a consequence, we partnered with the Spark community on the data source v2, and right now we support batch reads and writes. You can also point your micro batch stream to an Iceberg table, and even more, you can use Iceberg table as a streaming source to consume changes out of it. Around the same time, we added support for Flink, including the upsort functionality, Hive, Dremio, Trino, Snowflake, EMR, Dataproc, Athena, a lot of other vendors as well. So right now we have a rich set of connectors which you can choose from, which gives you a lot of flexibility. So you can use Spark for heavy lifting, and then you may choose to use Dremio or Trino for ad hoc analytics, all on the same table. We also added support for metadata tables, which is a distributed way to query your table metadata It is a really powerful feature, allows you to build a lot of services that are related to table management. Overall, there are like 16 tables at the moment, and they provide insights into different aspects of your table state. So you can see all of the statistics about data files, about partitions, snapshots that are available, history, and so on. So in this example, I'm selecting from the snapshots metadata table, and it gives me information about when a particular snapshot was committed, its ID, operation, and then a quick summary of how many files I added, how many files are removed, and so on. There will be another talk by Zihan on metadata tables. I suggest that you watch that one too. It will be a deep dive. It will explain all types of metadata tables you have and when to use which. So that should be really helpful if you're into Iceberg. We also worked on high-level SQL procedures to manage tables. So at the moment, you can optimize data where you can pick between bin, packing, sort, and Z order. You can also rewrite metadata so that it's properly aligned with your partitions and your job planning works as efficiently as possible. You can also expire all snapshots, delete orphan files, and roll back table state. So there are actually a lot more, which I won't be able to cover. In this example, I'm expiring snapshots that are older than a particular timestamp, and I do that with plain SQL. And then under the hood, that would be a fairly complicated process of figuring out what files can be deleted from the storage. There's another talk by Russell that will focus how you can use these procedures to manage data files and how you can do data compaction. And also you can watch another talk I gave in 2021 that would be a deep dive into these extensions that would cover all sorts of extensions and when to use them. All right, so we talked about how we made Iceberg production ready. Now let's talk about the ongoing phase of supporting more and more data warehouse use cases on top of data lakes. The first area is row-level operations. There are a few common use cases here. You may need to delete a set of records for regulatory compliance, or you may need to correct records because of an issue in the ingestion pipeline, or you may need to populate changes to your Iceberg table from other sources. And those changes may not only include inserts, but also updates and deletes. In that case, you can use the merge command, which is a very powerful tool, allows you to perform all those three operations in one transaction. Iceberg provides you a lot of flexibility when it comes to encoding row-level operations. We support copy and write, which means we rewrite data files if there are records that have to be changed. Works really well for bulk operations, but we also support merge and read, and actually two types of merge and read. The first one is using position-based delete files, and the second one is based on equality. Each of these three approaches have their own trade-offs, but you can pick between these in different engines, and you can use all three in the same table, so it's not predefined. It's a fairly complicated topic, so if you're interested in it, you can also watch another talk from 2022 that dives into how to tune row-level operations in Iceberg. And if you're into Spark, there's also a Spark presentation about the ongoing effort in Data Source v2 to support those operations natively. I'm also excited to announce a few features that are coming in 1.2 that is about to be released. In particular, we added support for storage partition joins. So if you have two tables that are partitioned in a compatible way, and you need to join those tables, you can now do so without any shuffles. And that also applies to your aggregations, and it actually works for delete, update, and merge. So this is the key to enable shuffless merge operations in Iceberg. There is one Spark limitation at the moment in 3.3, and it should be fixed in the upcoming 3.4. So once Spark 3.4 is out, you should be able to use truftless merge operations in Iceberg. We also added support for aggregate pushdown. So if you're doing aggregates on top of an Iceberg table, there is a very high chance that we now can push some of that work into Iceberg metadata because we store a lot of min-max statistics about the count, the record count, and so on. If this happens, then you can circumvent a lot of execution and save a lot of time. We also added support for change data capture in Spark. So we added the changelog table, which you can query either through SQL or through the data frame API. And you can also configure your start and end snapshots, either through timestamp or through snapshot IDs. If you query this, then you would essentially get a data frame where you would have your data columns, in addition to a few metadata columns that indicate like the change type, change ordinal, commit snapshot ID. At the moment, if you query, you would get inserts and deletes because there is no concept of an update in Iceberg. An update is a delete followed by insert. So this is what you would get if you query the changelog table, but we also will provide you a utility to compute pre and post images on the fly because you can reconstruct them if you know how the table format works. So you'll be able to access the full changelog, and the important part about this design is that we don't store anything extra in your table. We don't store that changelog next to your table. It is computed for you on the fly. We also added support for branching and tagging. So you now can create branches in your Iceberg tables, and then you can commit to those branches. You can perform some operations on them. And if you're confident that like this is the correct change, you can cherry pick that change into your master branch. So essentially, this will make Iceberg table act like a Git repository. There are also a lot of other features that are still in progress. A lot of them are related to ease of use. So we changed some of the default values that didn't really work that well. Also, there was a problem that you needed to change and configure Iceberg tables to get reasonable performance. And we're trying to fix that as well. So we know about that problem. So some of the default values didn't really work that well. Also, we're providing more utilities for advanced table analysis so that you can be really on top of what's going on in your table. We're also finishing V2 table maintenance. So we will provide compaction for delete files and expiry of delete files. Right now, it's kind of limited. We're working to solve those problems. We will also support end-to-end encryption from catalog to metadata to data files, so that you can check the integrity of your table and make sure that nobody corrupted your table. We also have ongoing efforts around secondary indexing. Right now, we support zone maps, but we also plan to support Bloom filters, inverted indexes, and dictionaries per file in the metadata. So that one's still ongoing. We also want to support the view catalog. Right now, if you create a view in Spark, that view is not accessible in other engines like Trino, because each engine has its own form to define the form of the view and its own representation of the view. So they are not really compatible. And we will provide a view catalog, which would make those tables, would make those views compatible across engines. And on top of that, we can build support for materialized views as well. And last but not least, we're also working on dynamic partitioning because Iceberg tables can have multiple specs active at the same time, you can actually build dynamic partitioning in a sense that if you detect that some partitions are too large, you can decide to split them into smaller subpartitions on the fly. Um, that's all I wanted to cover. There's another talk by Ryan Blue later today about what's new in Iceberg. It will dive more into these newer efforts and will explain some of the use cases related to these features. So I would suggest you attend that one too. It would be like a continuation of what I just talked about. That's all I wanted to cover. I wanted to finish with a few key takeaways. So even today, Iceberg allows a lot of data warehouse-like use cases on top of data lakes, but there are also a few gaps. And I predict that in the next couple of years, a lot of features that you will see in Iceberg will be performance and ease of use oriented, because that's probably the areas where we have most of the work to catch up with data warehouses. If you want to be part of that journey, we always welcome a new perspective in the community, and we would love you to join that community as well. Um, and thanks for your attention. If you have any questions, I will be glad to answer them.